So today I'll be talking about some of our recent work on identifying learning rules from neural network observables. One of the tenets of modern neuroscience is that the brain modifies its synaptic connections during learning to improve behavior. However, the underlying plasticity rules in the brain are currently unknown. And many proposals have been suggested, ranging from Hebbian style mechanisms that seem biologically plausible but haven't been shown to solve challenging real world learning tasks, to backpropagation, which is effective from a learning perspective, but has numerous biologically implausible elements. A major long-term goal of computational neuroscience will therefore be to identify which of these routes is most supported by neuroscience data, or to convincingly identify experimental signatures that reject all of them and suggest new alternatives. Along the route to this goal, it's going to be necessary to develop practically accessible experimental observables that can efficiently separate between hypothesized learning rules. So suppose you could measure a set of neurons in a circuit over the course of learning. What would you measure to identify the plasticity rule operative within that circuit? Would you measure postsynaptic activities from each neuron, synaptic strengths, relative changes between pre and postsynaptic activity? Would you additionally differentiate by cortical area? This turns out to be a substantial problem because it's difficult on purely theoretical grounds to identify which patterns of neural changes arise from given learning rules without also knowing the overall network architecture and loss function target, if any, of the learning system. So in this work, we take a virtual experimental approach to this question with the goal of answering whether it's even possible to generically identify which learning rule is operative in an artificial neural network across a wide range of possible learning rule types, system architectures, and loss targets. And if it is possible, which types of neural observables are most important in making such identifications? To do this, we consider over 1,000 neural network training experiments, which span learning rules involving variants of backpropagation and layer local alternatives, on both supervised tasks across visual and auditory sensory modalities and self-supervised ones, with 10 convolutional neural network architecture types of varying depths and 12 hyperparameter settings for each learning rule, ranging over batch size, model filter seed, and dataset randomization seed. We then measure statistics aggregated across units from each layer of the models. These are gathered from the weights, activities, or layer-wise activity changes over the course of model training. We then transform these with simple functions prior to computing statistics across units. And for each transform, there are 7 total statistics. We then use these collected observable statistics as features from which to train simple classifiers, such as a linear SVM, as well as nonlinear ones, including a random forest and a 1D convolutional 2-layer perceptron. These classifiers are then tested on held out data, and we consider various types of generalization to simulate experimental realism. First, is this general problem of identifying these learning rules on the basis of these statistics even tractable? Turns out the answer is yes. So across all classes of observables, the random forest, which is a simple nonlinear classifier, attains the highest test accuracy, and all observable measures perform similarly under this classifier. We next explore experimental realism in several ways. First, it's not immediately clear whether our approach will generalize to unseen architectures and learning curricula. This is particularly relevant for mimicking experimental realism, since if a new, quote, animal were added to our study, we ideally do not want to be in a position where we have to completely retrain the classifier or have the conclusions change drastically, nor do we want the conclusions to be highly sensitive to training curricula. Indeed, we see both generalization to held out architectures as well as to held out training curricula. Now, the results presented so far were obtained with access to the entire learning trajectory of each model, but often an experimentalist may collect data throughout learning at regularly spaced intervals. So we capture this variability by randomly sampling a fixed number of points at a fixed temporal spacing for each trajectory, which we'll refer to as subsample period. And we find that across observable measures, the robustness to undersampling of the trajectory is largely dependent on the subsample period length. As this length increases, depicted in the middle and rightmost columns, the classification performance increases compared to the same number of sample points for a smaller period depicted in the leftmost column. Finally, there are many recording paradigms in neuroscience, each with some range of unit subsampling and measurement noise. Therefore, we ask how noise and subsample robust are particular observable measures. To account for these trade-offs, we modeled measurement noise as an additive white Gaussian noise process added to model units prior to computing these statistics. And then reported here is the classifier's average test accuracy on these collective statistics on varying levels of unit subsample and Gaussian noise standard deviation. This data suggests that if one collects experimental data by imaging synaptic strengths, it is still crucial that the optical imaging readout not be very noisy, since even with the amount of units typically recorded currently, on the order of several hundred to several thousand synapses, a noisy imaging strategy of synaptic strengths may be rendered ineffective. Instead, current electrophysiological techniques that measure the activities from hundreds of units could form a good set of neural data to separate learning rules. Recording more units with these techniques can improve learning rule separability from the activities, but it does not seem necessary, at least in this setting, to record a majority of units to perform this separation effectively. So in conclusion, we show that we can identify learning rules solely on the basis of observable statistics without knowledge of the architecture or the task, and that this holds across various scenarios of experimental realism that we considered. Our overall hypothesis from this work is that in vivo recordings of postsynaptic activities on the order of several hundred units measured semi-regularly may provide a good basis on which to identify learning rules. We've made our code and dataset publicly available so others can analyze these properties without needing to train networks themselves. And we're also interested in collaborating with experimentalists to explore some of the hypotheses in our paper. So if you're interested, definitely feel free to reach out. Thanks.
Wonderful. Thank you so much, Aran. Here's some applause from everybody in the audience. So if you have questions, please type them in the Q&A. If it's too much to type it, just raise your hand and I'll promote you as a panelist and you can ask your question directly. In the meantime, maybe I can ask the first question. And I'm wondering, so if you have already these decision rules, well specified, you're showing you can distinguish between the two of them, but are there like qualitative signatures within the postsynaptic activity that even without a lot of modeling, you can say, well, this is a signature of one versus the other, or is it not as simple as that?
Yeah, absolutely. So taking a quantitative approach was our goal. One nice thing about the random forest as a classifier is actually, so we compute various statistics from the activities or from the weights, et cetera. And we can actually get feature importances. So importances of relative statistics for the classification problem across all separations that we've done. And what we observe is actually that there are certain statistics, that subsets of statistics from each type of measure that matter more, and we can actually weight them. So what that suggests is, if you were to say collect data from a set of units, you may not need to, do so many statistics basically on those units to be able to identify the learning rule within that system. Most likely just a small subset. And we identify those in the paper, but yeah.
All right, thank you. That makes a lot of sense. All right, so we have a question in the Q&A from Ari Benjamin, who is asking, did you look into which statistics were important in the random forest splits?
Yeah, absolutely. So let me see, I believe, okay, if I just share my screen, I think I can show you. So here we go. So, okay, hopefully you can see this, but basically, this is an example of the statistics that we see. So for each observable measure, weights, activities, or layer-wise activity changes, we have our combination of statistics that we have, and on the y-axis are the feature importances. So one thing we also kept track of was a rough layer position from which the statistic was measured from. We didn't find that to be very important. So that's here in the layer position column. Among the weights, the median seemed to be very helpful as a statistic. And among the activations, the norm, or the absolute, taking the absolute value of the activations and then computing the norm across units was seemed to be very relevant, but norm seemed to be a relevant statistic. And then finally, for the layer-wise activity changes, taking the square or the absolute value prior to computing this quantity seemed to be important. So magnitude, basically, rather than sign, seemed to be important there. But this is just from interpreting the random forest importances, which should be taken with some grain of salt as well.
All right, great. Ari, do you want to follow up? Nice cat, by the way.
I think that answers that question for me. I do have a separate question I can ask, which is that you've taken a classification approach, and in a novel biological system, we'd probably want to de novo identify what the learning rule is, not having a preset list. I'm sure you've thought about that extension. I'm just curious of your thoughts.
Absolutely. One reason we took the classification approach actually is actually so that which can be potentially useful for a downstream sort of more generative approach where you actually posit a form of the learning rule more explicitly, is that we actually didn't even know starting this work what we should measure. And so one goal of this endeavor was just to get our bearings on where we should focus on first. Should it be weights, activities, layer-wise changes, cortical depth, etc. It seems that the activations contain a lot of that information. They're pretty robust across a variety of scenarios that we considered. So that seems to be a good place to start if as a next step, if one wanted to then start to build more generative approaches. But our goal was really just to ask the very basic question and try to answer as best as we could in our setting of what to measure across a wide range of architectures and tasks and learning rules.
All right, wonderful. We have another question in the Q&A from the Hare. Thank you for your talk. As far as I understand, all learning algorithms used in the study were gradient-based learning. Is it possible to differentiate non-gradient-based learning rules from this family of gradient-based learning rules?
That's a great question. So all of our learning rules are gradient-based up to some modification. So the SGDM and ATOM are definitely gradient-based. Information alignment and feedback alignment operate on a pseudo gradient, which I think is still like a high dimensional error signal, but isn't exactly a true gradient. The reason why we chose those learning rules was that it allowed us to be able to train lots of models at scale to kind of basically be able to do data science on this question. We don't have yet a good theory of neural network learning to be able to outright ask and predict what the answer to this question might be. So we took an empirical approach and therefore needed a lot of samples to be able to really robustly identify these things as much as we could. But certainly you could apply this approach to other learning rules maybe without a gradient and ask the very same question. There has been prior work which motivated some of ours, theoretical work on single layer perceptrons with Hebbian learning rules that seem to indicate that weights and activities were relevant things, statistics or unit averages from those things were relevant to identifying learning rules, even in that context, or at least separating between, say, Hebbian learning and node perturbation, for instance. So that work is actually what it motivated us to try this more at scale, but certainly.
All right, great. And we have time for one last question from Pierre or Han. Have you constrained, and would it make sense to constrain the weights and activations to be similar to in vivo observed weights and activation distributions, sometimes observed to be log normal?
Yeah, I think you certainly could. We haven't examined our, and I think it's something that's worth doing. Really, is actually examining the distributions explicitly of the units that we've collected.